Hello everyone, this is Bradley. So today we're going to make a DNA with the correct base pairing. So you know that in our DNA, the coding is very specific that we have AT and GC. This base pairing is very important for you to code a protein or polypeptide because you need 3 codons to determine a correct amino acid being used in the sequence. So yeah, whatever. Okay, so let's just start with the plane, and then let's just start with a mesh line, just to shoot that to sky. I'll probably just delete these group inputs, and then we're going to point instance. Basically, the concept, the idea, the principles comes from animation nodes. So I'm just repeating the same process. Here, if we try to do this, even the resolution is 2, it's still a triangle. So we're going to resample the code to be 2, so that we're having this line. Why I don't use mesh line? This is because sometimes curve is better to work with, and then plug the combine XYZ. Actually, let's combine XYZ should be fine, and then increase the count. Let's plug this mesh into the stop and use the stop mode instead, and 0.1. So now we have this helix. Let's just decrease. Let's use the endpoints. Yes. And then let's turn this stop a little bit back. Yes, then this is fine. Okay. So once we have this, let me think what's the next step. Oh, the next step is the helical connection. I've discussed this preset in my expanding helix tutorial already. To do that, you need to realize the instances first and then plug that into sample from. So the length count will be your straight line, and the branch count will be your circle. So now we created a single curve line, and let's use a bevel curve to visualize that. Okay. And you just duplicate that and hit FFF, so you now have a double helix being done. So next I think is to instance all this kind of base pair. Talking about instance in base pair, there are several things that I would like to say. One is I'm going to, because there are probably many different ways to deal with the color, but the most efficient way I think in this particular case is just to manually create a kind of 4 cubes. So let's just go to the edit mode and edit a cube. Okay, so something like that should be enough, and we can definitely just decrease its scale. And then I'm going to add a material, select a color, then I'm going to duplicate this and add a new material, take that to green, duplicate and add a new material, take that to blue, duplicate, add a new material, take it to pink or purple, whatever color. Okay, and then these are 4 cubes generated are DNA pairs that we're going to instance. So you just call that nucleotide or whatever stuff. Let's just say that NU. Okay. So yes, the next thing is we're going to take these kind of points. I'm going to use the separate geometry, separate these realized instances, and I'm going to use the preset called index mask fourth, because the index of this kind of point being generated is 0, 1, 2, 3, 4, 5, something like that. Okay, in this case, just use the default should be good enough, and we can actually see that. No, we cannot see that. Can we try to curve the points? Yes, we can visualize the points in such a... Oh no, the point size is too large, isn't it? Yeah, anyway. I think I'm just going to directly... is there set point radius? No, there's no way to really visualize, I think. Yeah, anyway. Oh, bevel curve should work as well. No, not working. Also, so, okay, unfortunately, I do not know how you visualize that. So we're going to just move next step to instance. And then I'm going to take a collection info from our nucleotide. Actually, this is a base pair. But anyway, I'm going to enable separate children's, reset children's, take that to instance, pick instance, select the object. So now this is what we are looking at. We need to deal with the orientation of them. So here, what I'm going to do is to take the position and then vector mass. We're going to ignore all this kind of z-axis, so let's just take a z-axis down. Okay, multiply by 0, align rotation to vector, put the vector into place, rotations into z. So now we can actually see that. So here, because we're looking towards outside, if you compare to the curve that we've generated. So in this case, we just take the factor to -1. So they are looking inside. The resolution is actually too high. So let's just decrease the count. Something like that. In this step, we can definitely turn the scale down. Something like this should be enough. You can definitely control the scale better with all this kind of vector mass. But in this case, I'll probably just keep it as it. No, probably I still would like to change that. Otherwise, this looks something weird. You can increase thickness by increasing the XY value. Okay. And very importantly is to actually look at the color you generated. So this is what happens. So here we're going to instance on the other side. So we just use the inverted points and use the same instance. And plug the instance to join geometry. Plug the same rotation. Actually this rotation. Oh yes, rotation, not the scale. So rotation to rotation. So now we have everything's being matched up, but they are the same. So we need to make them opposite. The way we're going to do is to determine the index. Previously, I've already made a tutorial talking about how controlling the index will help controlling the object from the collection. So here, let's firstly create a rule within the first index. So we take a random number and plug it integer. Since we only have about 4 objects and index always starts from 0, so we goes from 0 to 3 and plug the value. So we have randomized our left parts of this whole thing. It's kind of very interesting. So in this case, you just change the seed, I guess. Yeah, something like that. So you try to break it up more so that it feels like random. Okay. Then next is we're going to create a condition so that the opposite index must be corresponding to the original one. Okay. So this is a little bit tedious part, and there's one important problem with the switch node is that this switch does not receive any field, so you will have a bug report, not a bug report, and warning. Okay, I think they will try to improve that in the future, but at this moment you cannot do this. Instead, I'm going to use a preset I made for mixed float. Okay, so here we're going to do several conditions. So one is compare float. So here the base pair I think is 1 pair to 0 pair to 1, 2 pair to 3. So this is the base pair that we're going to work with. Okay. So what we're going to do is, if our random value equals to 0, then we are going to output the float b, because this is the factor. If it's equals to 0, then we pair with 1. If it's not, then we make another condition. In the second condition, so in the second condition, we know this must not, the random value must not equal to 0. Then it may equals to 1. If it equals to 1, then we pair with 0 and plug that to A. Third condition, this is our last condition. So if this equals to 2, then it will pair with 3. Actually, yes, never try to plug everything into the climb factor, it will just bug. So if it equals to 2, then we output 3. Otherwise, the only condition left is when this index equals to 3, which it should pair to 2. So once you have done that, you just output this value to the instance index. Then you can say, see that purple is always paired with blue, red is always paired with green, and this is it. So you can deal with the color better or other things. And you can even make this kind of setup a little bit more complex. For example, adding more kind of a phosphate backbone, or the ribonucleic deoxyribose on this backbone or whatever stuff. Yeah, but this is approximately it. There's one more question I would like to discuss, is this kind of floats, is this rotation. So during DNA replication or other process, what we need to do is to unwind this DNA helix. So we need to offset the rotation. So here let's take I think a directional fold. Actually, in reality, it's more likely that you're going to have proximity fold, because you do not unwind the whole length of DNA, you unwind a part of that most of the time, which is called kind of replication fork or replication bubble, whatever stuff. But anyway, you don't necessarily understand what I'm saying scientifically. It's just kind of a little bit whatever. This is, we're going to change so the index always starts from 0, so we're going to evaluate on z, so just take that to z. And this is how it works. This is very jaggy, so we increase the size so that make it a little bit smooth. Hey, then we unwind that. Hey, yeah, then we unwind that. Hey, it's kind of very fun. Since we're unwinding the DNA, it might be even important if you separate them up. So in this case, we're going to combine x, y, z, take one on y and z, but separating on x-axis, because I think x-axis is responsible for separating them. Okay, so here let's just take so we're going to map range. So the original scale is 0 to 1, so the minimum is 1. I'm going to take the maximum, the others. So okay, this is actually not right, so we probably need to reverse it. So the maximum is 1, the minimum is 5. Actually, we probably need to separate the fourth a little bit. So we're going to separate the fourth using the same directional fourth, but with a location offset probably for -2, +2. Yes, probably -10. So we unwind that, and then, oh, it's being separated. I'm not going to make the full animation because I'm not yet also sure how to make the replication or transcription going on this segment. But I think yeah, this is interesting already. I don't expect that this becomes a true scientific animation. But anyway, so I hope you enjoyed this video. I'll probably see you next time. Bye bye.